Hello, let's begin today's lecture session on sequence and series. In the past few sessions, we had been talking about sequence, and we have actually finished sequence as per our course syllabi. So today onwards, we will talk about series, rather infinite series. So as we proceed with understanding of infinite series, let's see what are the topics we will look into in today's session. Firstly, we will look into the definition of infinite series, then the concept of sequence of partial sums, and this will be continued to understand convergence or divergence of series and some examples. So, what is an infinite series? Let an be a sequence, then the infinite sum summation n equal to 1 to infinity, that is a1 plus a2 plus dots plus an plus dots, is called an infinite series or simply series. So we see that an infinite series or just a series is nothing but a sum of infinite number of terms of a sequence. Let us see some examples. The first one here is 1 square plus 2 square plus 3 square plus it continues plus n square plus again continues. So in the summation notation, this is summation n square n equal to 1 to infinity. So the sequence here is an, where the nth term is n square. That is, this is the sequence of square of natural numbers. The next one, the terms of the series are now 1, minus 1, plus 1, minus 1, plus 1, and so on. So in the summation notation, this is summation minus 1 to the power n minus 1, n equal to 1 to infinity. Now, as we observe that an infinite series, or rather series, is a sum of infinite number of terms, the natural question which comes to our mind is, what is this sum? Because we are adding an infinite number of terms, is the sum also infinite, or there is a chance that the sum can be finite? Now, all these questions can be answered with the concept of convergence or divergence of an infinite series. So we proceed to look into that, but in order to define a convergent or divergent series, we would like to define first the sequence of partial sums. This concept will be actually needed for the definition of convergent or divergent series. So what is this? Let's see. So given a series summation n equal to 1 to infinity, let us define the following. S1 equal to A1, so it's just the first term of the series. S2 equal to A1 plus A2, so the sum of the first two terms. S3 is the sum of the first three terms, that is A1 plus A2 plus A3. We continue like this, so Sn will be naturally now the sum of the first n terms, that is summation ai equal to 1 to n. Now observe that this S1, S2, Sn, all these have been formed from the series by taking partially terms from the series, right? So naturally we call Sn as partial sums, and notice that this Sn will form a sequence as n goes from 1 to infinity. And this sequence is now called the sequence of partial sums. Let us now move on to define convergent or divergent series. So firstly, convergent series. A series summation n equal to 1 to infinity is said to be convergent and converges to L if the sequence Sn of partial sums is convergent and limit Sn n tends to infinity is equal to L. So what do we see? See that the definition of the convergent series is totally dependent on the convergence of the sequence of its partial sums. So if the sequence of partial sums is convergent and has a finite limit L, then only the series is convergent and it converges to the same limit L. Also note one more thing, that Sn is a1 plus a2 plus an. So as we take the limit of Sn as n tends to infinity, it becomes nothing but this infinite series summation n equal to 1 to infinity. So then this limit L actually gives nothing but the sum of this series. Next, we look into the definition of divergent series, and it's very much similar. A series summation n equal to 1 to infinity is said to be divergent if the sequence Sn of partial sums is divergent. That is, if limit Sn is plus infinity or minus infinity. So once again, we need to check whether the sequence of partial sum is divergent, and if it is so, then the series will be said to be divergent. The third type is oscillatory series, and the series summation n equal to 1 to infinity will be called oscillatory if the sequence of partial sums is also oscillatory, or otherwise if the sequence of partial sums is neither convergent nor divergent. So, understanding this definition, let's now proceed to see some examples where we will check whether a given series is convergent or not. So the example here is, determine whether the series 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus 1 by 4 into 5, it continues, plus 1 by n into n plus 1, plus it of course continues again, converges or diverges. Now, as we have seen just now the definition of a convergent or divergent series, we can understand that we need to check the convergence or divergence of the sequence of partial sums for the given series, right? So, let us first construct the sequence of partial sums Sn as per our notation. And as per our notation, Sn is a1 plus a2 plus an. The nth term over here is of course this 1 by n into n plus 1. So let's write down that. So Sn here is, as just now I told, this expression. And now let us simplify this. Now note that 1 by n into n plus 1, that is equal to 1 by n minus 1 by n plus 1, isn't it? So this is for the general term, the nth term. So of course, all the terms we can write, we can split up in this way. So 1 by 1 into 2 is 1 minus half. 1 by 2 into 3 is half minus 1/3. 1 by 3 into 4 is 1/3 minus 1/4, and so on. Now, as we want to simplify this, we observe that here minus half and plus half will cancel out. Minus 1/3 plus 1/3 will cancel out. So in this manner, actually all the internal terms will cancel out. We will be only left with the first term 1 and the very last term minus 1 by n plus 1. So finally, Sn is 1 minus 1 by n plus 1. Now, of course, we need to check the limit of this sequence. So what is that? See that limit Sn n tends to infinity will be actually 1. Why? Sn we have just now seen is 1 minus 1 by n plus 1. So as we take the limit n tends to infinity, of course 1 by n plus 1 tends to 0. So this limit is nothing but 1, which is a finite number. So what is our conclusion then? Of course, we can now conclude that this sequence of partial sums is convergent, and therefore by our definition of convergence of a series, the given series is also convergent, and of course it converges to the same limit 1. With this example, we will close today's session. In the next session, we will continue with some more examples and some properties of infinite series. So thank you and goodbye till then.